Hi everybody, in this project we present StegaNeRF, embedding invisible information within neural radiance fields. Neural radiance field, doubled as NeRF, has attracted increasing attention due to the photorealistic performance of novel view synthesis. And in NeRF pipeline, here's a radiance field, fitted by MLP. It maps every position and the viewing direction in a scene to its color and volume density. And the volume rendering further enables figuring out the color of a camera ray that we can observe. Besides, NeRF represents scenes through network weights and allows efficient storage and sharing. So, coming a trend for people to upload and exchange NeRF assets on online platforms like Luna AI. However, some risks like piracy may hinder this vision. Like an attacker can illegally copy others' distributed NeRF and re-upload it in his credit, and the copyright is totally unprotected during this process. So a pipeline is to identify and claim the copyright of distributed NeRF is highly required by community. Look back to 2D images. Such a piracy risk is alleviated by applying StegaNeRF, which embeds invisible information like hyperlinks, pictures, and etc. into the host images and even some AIGC. However, such StegaNeRF pipeline has yet to be built on NeRF, and we signify an initial exploration. Our technical goal is to instill customizable, imperceptible, and recoverable information into NeRF rendering at any viewpoint, and meanwhile without sacrificing rendering quality. So great, but how to do it? A straightforward solution is to directly lift 2D steganography to 3D NeRF, and people can apply 2D steganography on clean multi-view images to get stamped ones and use them to train NeRF. Then the only remaining question is whether the encoded message can retain on the novel view rendering. Unfortunately, we find the answer is no, and the embedding finally gets lost in the rendering at the novel views. And we also visualize the residue errors against the original cleaned counterparts, which implies the hints of hidden information. And we find such hint ends up changed and corrupted in the rendering. To tackle it, we present a novel optimization-based steganography framework called StegaNeRF. First, we have a standard NeRF from standard NeRF training, by which the weights of our StegaNeRF are initialized. Then, for the renderings at every training pose P, we apply a consistency regularization between the renderings of the StegaNeRF and the standard version. Moreover, we introduce a decoder to recover pixel-wise hidden information from StegaNeRF rendering. And finally, to avoid false positive recovery from standard NeRF, which is not required to enable steganography, contrastive constraint is applied to decode not hidden images but empty messages. To further compress the trade-off between hidden message and preserving rendering quality, we present two novel designs from different perspectives. And the first is classifier-guided recovery to improve recovery results of hidden. The insight is accurately recovering all the pixels may be challenging for a decoder. So we introduce an easier task of classifying the model source of renderings and take it an extra guidance of input to decoder. The second is adaptive gradient masking to enhance NeRF rendering quality after hiding some information. The insight is NeRF shows not equal value to overall rendering quality and exhibits strong plasticity by identifying more significant weights and masking out their gradients, and thus minimizing their parameter update. The message is adaptively hidden into less important model weights. We deploy StegaNeRF on several usage scenarios, and over here we pick two featured ones. First is embedding hidden information in a scene. We report results on the nerve rendering and the hidden recovery, and the standard nerve is picked as upper bound rendering results. Two typical 2D StegaNeRF methods both fail in encoding message in nerve, with poor SSIM scores. In contrast, StegaNeRF achieves promising recovery with only minor drop in rendering effect. From visual results, StegaNeRF generates perceptually identical renderings as StandardNeRF, and the hidden images can be recovered from different viewpoints of nerve consistently. Moreover, we embed multimodal signals, include image, audio, and text, all within a single nerve model. The multimodal information can be encoded and recovered successfully. And this feature not only supports creative nerve deployment, but also opens an interesting research direction of applying nerve as multimodal data representation. Okay, that's all. Thank you for your time. The website, paper, and the code for this project are all available online. Please see them for more details.